Hello and welcome to today's chapter, which is chapter 9.7 on alkyne hydration. So if you remember, previously in our hydration studies, we were taking some kind of alkene, reacting it with dilute acid like H2SO4 and getting a Markovnikov alcohol group. Similarly, we could take, and let's just write this, Markovnikov. Similarly, we could take an alkene and add BH3 THF adduct, and then H2O2 and sodium hydroxide to give us the anti-Markovnikov alcohol. Now today, what we're going to learn about is what happens when we take an alkyne and submit it to hydration conditions. It turns out that if we add dilute acid to an alkyne, that we end up getting a hydration product or more specifically, this product, but it is very slow. And the reason why we get a very slow hydration with dilute acid is because we go through this intermediate, which is very high energy, because that carbocation is not stabilized by any resonance, as we talked about in chapter, I think that was 3 maybe? If not 3, then definitely 6. So to speed this reaction up and actually stabilize that carbocation, what we're going to do is we're going to instead add a catalyst. So in this case, we're going to take an alkyne and we're going to add our dilute acid, say H2SO4 again, but then also a catalyst like mercury with a 2+ charge. And if we do that, then we will get this ketone product. And how this works is that first the alkyne attacks the mercury to give us a mercury compound, now with a plus charge, and this vinyl carbocation. Now remember, a carbocation in this structure is still not very stable, but lucky for us, the mercury has a lone pair that allows us to make this mercurinium ion. With the 2+. And this ion is much more stable, has a partial positive on the carbon, but the carbon is formally neutral. So we're going to call this a mercurinium ion. So once you form the mercurinium ion, then we can start doing the hydration chemistry that we know so well. Because like we said before, in dilute acid, there's a lot of water around. So one of those waters can attack the vinyl carbocation to give us this positively charged oxonium ion with the mercury still attached to the double bond. But once we get to this point, now we can have a water take the proton from the oxonium, stabilizing our molecule. And once we've made this, now the hydronium ion that we just created can do our hydration chemistry just like we're used to, where the double bond attacks the hydrogen, giving us a carbocation. But this carbocation is not very stable. And so you have a resonance form to try and relieve some of that instability. But unfortunately, the resonance form is also not that stable. I'm actually going to draw it the other way because it's too, there we go. The resonance form is also not very stable. We'll change the color, that way we see the resonance form. Okay, so here's our mercury. There we are. So again, this is a positively charged oxygen. Really, oxygen does not want a positive charge. So what's going to happen, instead of having these two relatively bad resonance forms, the mercury is just going to eliminate, giving us now something that makes a lot more sense, which will be what we're going to call an enol, because it's an alkene that is also bonded to an alcohol on the double bond. And this is a special molecule because the enol has what's called a tautomerization event that happens, where it rapidly interconverts between this ketone molecule here. And they both have neutral molecules all around, so this is allowed. But the ketone is typically the one that is present in the highest concentration. So once you make the enol molecule here, it rapidly tautomerizes to the ketone. So that's why when we say we are doing a hydration of an alkyne with a dilute acid like H2SO4 and a catalyst like mercury, we make this ketone molecule instead of the expected alcohol because of tautomerization. So this is our Markovnikov product, remember? But what if we want to make the anti-Markovnikov product, as we showed before? Because with alkenes, we use BH3-THF. But the problem there is that if we use BH3-THF, what's to stop us, or what's to stop the reaction from continuing on once we have the double bond? Because if you remember, the BH3-THF, it added 3 times to 3 different alkenes. And alkenes are good substrates for attaching to a boron atom. So we need to find a way to stop the reaction at one addition. And one way that some clever people did this was by using a molecule like 9BBN. 9BBN has this structure, and what makes it special is that it has only one hydrogen. So whenever you, I'll move this, whenever you add, or it has one boron hydrogen bond. That's what makes it special. So if you add then an alkyne to this, in the first step, in the second step, you do H2O2 and NaOH just like normal. What you end up getting is the anti-Markovnikov aldehyde. So just so we know the naming, whenever you have a molecule that has a C double bond O and two carbon molecules or 2 carbon atoms attached to the carbon of this carbonyl group, this C double bond O group, that's called a ketone, as we just saw. And if you have one of those carbons replaced by a hydrogen, that's called an aldehyde. Right. So how this reaction actually goes or proceeds is that you end up making this intermediate. here. So once you make this one, then you use the H2O2 just like before. So I'll just write H2O2. The mechanism is exactly like the one we saw before for the hydroboration oxidation to give you eventually this enol. And once you have this enol, then you simply have a tautomerization event happen again to give you the aldehyde. And this is really the take-home message for this chapter, is that we have two ways to hydrate alkynes, either Markovnikov or anti-Markovnikov. One either with dilute acid and mercury, or one with a specialized boron reagent in a hydroboration oxidation event. So that was chapter 9.7.